Right, second half of the session, capacitor discharge. Not going to go through this in quite so much of a step by step because it is very similar, okay? But we've got our capacitor that's been charged up, and I've used the same values. Capacitor's been charged up to 10 volts. So I'm just going to put on here that that's been charged by a charge current in that direction. Okay, it's going to be discharged by a discharge current when we turn the switch on. I discharge in that direction. So the current's going to flow the other way. Okay. So at t equals 0, at the time when we close that switch, so we're going to consider it in isolation. At t equals 0, VC is 10 volts. What's VR? It's the positive side, negative side of that, been charged up, the current in that direction. What voltage have we got? We've got a voltage arrow there, current's going to go in that direction, so there's VR. What does it equal? We've got one clockwise arrow, one anti-clockwise arrow, they must both be the same. Yep. Okay. And in actual fact, all through discharge, little VC is equal to little VR. It's got to be. Yeah? Because the capacitor is acting like a little battery to that resistor. Yeah. And at t equals 0, how do I calculate I? And we're talking about, just clarify that, I discharge equals, how do I calculate that in this case? Must need to apply Ohm's law somehow. So what am I going to do? Yeah, little VC over R. 10 over 10 equals 1 amp. Yeah. So if we go down our graph route again, there's T. We'll make VC green. We'll start at 10 volts. And VR is the same. VC and VR are equal. And let's put our current here, starting at that point, 1 amp. Yeah. So they're starting at peak values, what values they had at the instant you switch on, and VR is going to have the 10 volts of the capacitor across it. Short period later, when VC has gone down to We'll go with 8 volts this time. So VC is down to 8 volts. Therefore, VR must also be 8 volts. And the current will be 8/10, 0.8 amps. Yeah. So after this short period of time, our voltages will have dropped down here somewhere, and our current will have dropped down here somewhere. Okay. And like the other one, speed this up a bit, we're going to get the voltage, capacitor voltage and resistor voltage as an exponential decay towards 0, never in theory quite getting there. So that's VC, and VR would take that same path, and then the current would also do that and not quite get to 0. So they both take, all the quantities will take an exponential decay path on discharge. Okay? So, formulae wise, for discharge, these are in your notes. VC is equal to VR, and both of them are equal to Vm, the maximum applied voltage, times E to the minus T over CR. And I is equal to Im, which comes from that's the maximum current that will flow at the time T is equal to 0 times E to the minus T over CR. Im equals current at T equals 0. Vm equals in this case Vc at T equals 0. Yeah. Vc after one time constant for our circuit Vc is equal to 10 e to the minus 1 over 1, and I think you'll find that should be what value? Anyone want a hazard a guess what a value is? It's not really a guess.
0.37.
No, 0.37.
63.
It's going to drop by 63%. So it's going to be, you're close with your 0.37, that's 3.7. Going to lose 6.3 volts. Yeah. E.g. lost 63% from start. Yeah. And if you've done all the calculations, you'll find if you go another time constant, that'll lose 63% of that 3.7 volts, and then 63% of the result of that, and so on, it carries on. And again, after 5 time constants, it'll be down, it will have lost 99.9% of its charge and therefore that's where we consider us completely discharged. Rule of thumb. Okay, and again on our graph, just going back to that, on our graph, if we carried on at the original rate of fall, we put this line in here again, original rate of fall, that's where T equals CR, the time constant, is for the discharge as well. So that's if we made the discharge current stay at 1 amp, we would get to 0 volts after one time constant. So the other one was if we carry on putting 1 amp in, we'll hit the 10 volts after one time constant. If we just carry on with the discharge current of 1 amp, we'll end up with 0 volts after one time constant. Okay? Now, one kind of calculation you might be asked to do here with this type of circuit is find the value of R, the discharge resistor, that will discharge VC below 1 volt. If you had a mains voltage system, 400 volt system, on a 400 volt mains, that capacitor could be charged up to as high as 565 volts at the point of switch off. So if you have, what's quite common on things that use high values of capacitance, motor inverters for instance, the switching off will drop a little relay out that will automatically connect the discharge resistor. And the idea would be that you design that so that we've got to a safe level in a certain amount of time. And extra low safe voltage, 50 volts. Below 50 volts is considered to be as safe as a battery. So you might be asked to design the circuit, put a suitable value of resistor in, such that you get below X voltage within a certain time. Below 1 volt in, let's say, 2 seconds in this case. So we've got the same circuit, but we're going to change the value of the resistor so that we guarantee that it ends up below 1 volt in 2 seconds. Okay? So the formula we're interested in is the formula for little VC. We know that's equal to Vm E to the minus T over CR. Right? This time we're interested in R. We need to get R out of that formula. How are we going to start by rearranging that formula? Divide by yeah, that's what we did before, don't we? I'm gonna write it like this. I'm gonna put E to the minus T CR over this side. Oh no, I won't bother. VC over VM is equal to E to the minus T over CR. Right, how do we get rid of the E to the power of, E to the power of X function?
Oh, use your ln.
Yeah, natural log of both sides.
What are you doing? Times divide.
No, it's not time. It's doing the natural log function of both sides. So, doing ln of E to the power of X, Paul, those two things cancel each other out. And you're just left with whatever. Those two things cancel each other out and you're left with 1. Yeah? They cancel out. So if you take ln of both sides, we cancel the E on this side. So what we've got then is ln of little vc over Vm is equal to minus T over CR. Anyone got an idea what the best thing to do with that is? I'm going to get rid of this. Any ideas? Bearing in mind we want we want R on its own, and we want it on the left-hand side. We can write. Would you flip it?
CR over minus T
Yeah.
equals 1 over ln.
Yeah. So what is that called?
Reciprocal.
Take reciprocal both sides. Turn them up the other way. Turn the fraction up the other way. Bearing in mind that this could be written as ln Vc over Vm divided by 1. So by doing that, we end up with 1 over ln little vc over Vm is equal to CR over minus T. Next, multiply by minus T. I'm going to take the chance to stick CR over on the left hand side now. So CR is equal to minus T over ln little vc over Vmax. And the last thing to do, divide by C. So we end up with R is equal to minus T over C ln little vc over Vm. Formula. Now can I put some numbers in it? We want minus 2 seconds, we said, is our time. C was 0.1 farads times natural log of, was it 2 seconds we specified or 1? 2 seconds, and below 1 volt, wasn't it? So 1 volt at 10 volts equals. So plug those numbers into the calculator, get a value, a new value for R that will see that capacitor discharged in that amount of time. Units. .691. In actual fact here, if you want to be really, really technical about it, you ought to round it down. Because the resistor being slightly higher than the actual value means that it will take a little bit longer. Do you get what I mean by that? The current would be lower, therefore going to be. So to be on the safe side here, if you're going to pick a value of resistor, you'd pick one slightly lower than that rather than one higher, because lower is going to discharge it quicker. Yep. Okay. So I'll just put a note down there. Note would be wise to select a value less than this in safety critical discharge circuits. Okay. And just to summarise the whole charge-discharge cycle, for one single circuit, there's put our graph on the page. For the current, yeah, during charging, the current does that. Put a dashed line here and say charge, discharge. During discharge, the current starts and it goes in the opposite direction. So if we're talking about a capacitor charging and discharging, the current does that. If that's where we switch over from charging to discharging, so immediately go from one to the other, that's what will happen. The current will reverse direction, start discharging the other way. So that blue is I. VC would start at nothing and go up to a maximum and then fall from there towards zero. VM IM. VR will do that. And then do that. Want it? So red is VR. Agreed? So, although we drew the current the same way when we considered it in isolation, if this circuit kept turning off and to charge, discharge, those are the shapes of voltage curves we'd get out of that circuit. And our current would reverse direction here and then get discharge in the opposite direction. Okay? Any other questions that you'd like to ask me about this? Happy to have a go at some. I think there's 4 questions at the end of this week's notes. Okay.